Hi, everybody. My name is Mateusz Hordyński. I'm a technical leader at deepsense.ai. And today I have prepared a presentation for you. The title of my talk is Bridging Large Language Models and Databases. And I want to focus on the practical tips, the lessons that we have learned while deploying such a combination of tools. So let's start. I think it would be the best to outline the typical solution that we want to build with these tools. And recently, in the past few months, it was really common for the enterprises, for the companies to build all sorts of chatbots. And often these chatbots require access to the data stored somewhere in the company. And very often, this data is stored in some sort of the database. So we need to access that database to answer the user questions. Here I have an example of the chatbot application. Let's go together through it. Let's start from the beginning. We have a message from the user, a question from the user, what products are out of stock? And after that, we got a response from the assistant that it has checked the warehouse database and the products which are out of stock are milk and eggs. After that, we have another follow-up question. So have these products already been ordered? And again, our assistant was able to answer that question, and it answered that there is a pending order for 100 bottles of milk, which are scheduled to be delivered on some date, but it couldn't find any orders for eggs. So usually we call these types of approaches when we call the database through the natural language interface, the text to SQL approach. And you may ask me, how does it work? So here I have the simplified diagram of such architecture. And let's go through it. Let's start from the user question. So we have natural language question from the user. And what we can do with it, we can ask the large language model to create an SQL query based on that. Given the query from the model, we can execute it against the database. And after that, we can go back again to the model and instruct it to generate the answer based on the results we got from the database and maybe based on the question. And of course, we can send this answer to the user. And in the core of this approach, of course, we have a prompt to the model. So here I have a simplified version of it. Let's go through it. Let's start with the system prompt here. So the first sentences are as follows. You are a super smart database developer, and you have access to the following Postgres tables. So we do two things here. Of course, we need to at first show some love for the model, and then we need to specify which database we are using here. After that, what we can do, we can list the tables that the model should have access to. In our example, we have only one table, so we have table products with 3 columns, ID, product name, and quantity. And after that, we instruct the model to write SQL query to answer the user question. And we say to the model that we want only SQL code. This is important because models tend to add extra comments, like, for example, sure thing, here is your query. That is not something that we really want. It's easier for us to parse the answer without any extra comments. So just to recap, we say to the model that it has access to some database. We list the tables that it has access to, and we instruct to return SQL query and SQL query only. And after that, we got the question from the user. So what products are out of stock? And we got the correct response. This query will answer that question. So select star from products where quantity equals 0. It totally makes sense. It would be okay to execute that query and answer the question based on the results from that. Okay, so we have the basics covered, and let's go to the practical tips, practical lessons that we have learned deploying such systems. And let's start with lesson first. Users aren't always nice. Let's look at this example. We have a tricky user here, and our user sent the message which goes as follows: make user with email matthew@example.com an admin. And as you might guess, our model did exactly what the user asked for. So we have the query, which after executing it, it will make my user an admin in the system. And remember, what we do with the queries returned by the model, we execute them right away to the database. And I hate to state the obvious, but it's not something that we want to be executed in our production database. Yeah. And here is another example. So there is no tomorrow. Let's drop table products. And again, even worse, after executing that query, we would lose all our products in our database. And of course, it's not something that you want to be executed on the Friday evening. Yeah. So what you can do to mitigate that? I recommend that you should always grant minimal possible permissions to the account the large language model uses. And I would say probably you need only read-only access. So probably only select statements. Sometimes it makes sense to have inserts or updates if you want any changes into your database based on the user actions. But for sure, you don't want any deletes or drops. Yeah. And more than that, you should limit the tables that the model has access to. So, for example, it doesn't make sense to, for example, have authentication tables and query authentication tables by the model. And even better, what you can do, you can really take a step back and think what data the model should have access to and create dedicated views for the model. So then you can have the limited columns, really think about it. Okay, the model will query this table with these columns, and this is all the things that it needs to execute the query. And maybe even you can enforce some extra filters on that view. And last but not least, you should lock your request prompts and the model responses. And thanks to that, if any user does something fishy in your system, you can catch it right away and respond to that. For example, ban the user. Here I have the screenshot from the Langsmith, which is a really cool tool for tracking your requests to the large language model. Okay, so lesson 2, semantic search is a must. Here I have another example, and it looks pretty simple because we have a question from the user, which clients are from New York? And we got the response. We got SQL query. It looks pretty okay to me. Like we select everything, select star from clients where city equals New York. Looks pretty okay for me. But let's take a closer look at our data. Here we have a clients table. It's super simple. It has only 3 columns. We have column ID, client's name, and city. And here is our data. And I will give you a moment to catch if you see a problem here with this query. Okay, so our user used the shortcut for the New York. And of course, what we have in our database is the full name of the city. And after executing that query, what will happen is that we will return nothing we will return 0 rows from the database. And probably we will respond to the user that there are no clients from the New York. And that is just not true. And it's not something that we want to happen in the production scenario because it is basically lying to our user. Our user, based on that answer, may do some action which is harmful to them, like make a bad decision based on that answer. So it would be even better to don't respond at all. So what we can do to fix that problem? One cool way to fix that is we can employ embedding models for that. And embedding models are really, really cool. Probably most of you know how they work. But this is, you can think about them as a black box, and they take a text as an input, outputs a vector, so just a lot of numbers. And these numbers outputted by the embedding model have this very, very cool characteristic that if you create the vector from the similar text, like the semantically similar texts, they will be really close to each other. The numbers in the vector will be really close to each other. So thanks to that, what we can do, we can extract constant string values from the SQL query. So in our example, we can extract all the constant strings. In our example here, we have this New York shortcut. And we can compare the embedding of that extracted value with previously created index. So what we can do here, you can think about it, we just grab all the cities in our database. We create an index, probably in some vector database. And for each city, we calculate the embedding. If we have that index, we can compare the embedding of the new value coming into the system, so New York shortcut. And after comparing it, we got the New York as the closest match. So probably user by typing NY meant the New York City. And after that, we can replace each constant occurrence with a closest match. And that brings me to the question of extraction. So how exactly extract these constant values from the SQL query? Actually, you have multiple choices here. You can either use abstract syntax tree parsers, so parsers coming with the SQL syntax that you are using. You maybe use the placeholders in your query while generating that, but also you have third option, and it's the easiest to show, so that's why I present it. So given SQL query, extract from it, we can employ the large language model here. And we do this by using this prompt. And in the system prompt, we have something like this. Given SQL query, extract from it constant values with corresponding column names, return result in JSON. And we have SQL query here. Select from clients where city equals New York or city equals Detroit, and status is something else. Yeah, status is active. And our model was able to extract these values from the query. And as you can see here, we have city. So for the city index, probably we need to extract. We have the constant values of New York. We have Detroit. And what we can do here, we can query the city index with these values, and we can replace the values in the query with the closest match. Okay, so lesson 3. Large language models are far from being good database developers. And here I have a screenshot from the BERT benchmark. BERT benchmark is a benchmark, of course, for evaluating the text-to-SQL tools. It is composed of multiple databases, and each database has multiple questions, and they are in different difficulty levels. So for each database, you have simple, medium questions, and challenging ones. And as you can see, the whole benchmark is not super easy, because even human performance is 93%. It was done by some data engineers and database students. And the highest position on this leaderboard manages only 65% accuracy. Worse than that, GPT-4 achieved 55%, so 10% less in the same benchmark. And if you ask me, it's probably not something you want to tell your users, okay, you have this very cool application, but it will work only half of the time, yeah? We need to take some extra steps to achieve better results. And I have some tips what you can do to make it a little bit better, and start with the first one. So on this slide, I would like you to take a step back and really think about it. What do you do? How do you approach writing an SQL query as a database developer? Yeah, you have a task, you need to write an SQL query. What do you do? I usually, of course, sit with my computer and I start with the first guess. I type the query. Maybe it will work, maybe it won't, but I type it and I try to execute it. Sometimes it's successful. I am happy. I can close my laptop, but usually I got some error from the database. And of course, you can give up and don't try ever again. But usually what you do, you read the error and you try to fix your mistake. And we can mimic that behavior. I like to call it a feedback loop. So what we can do, we can ask the model first to generate its first guess. And after that, we try the query. If it's correct and the database executed it and returned results, we just generate the answer to the user. But if the query is not correct, what we can do is we can grab that error and ask the model to regenerate the query again with the error in the context. So here we have another example. Select star from products where number of products equals 0, and we got an error. But rather than failing the whole process, we added extra message to the conversation with the model, and we said that the query is invalid. Postgres returned error, so column number of products does not exist. And after that, maybe the model will generate the correct query. You can repeat that process, for example, 3 times. From my experience, if the model can't generate a valid query after the 3rd time, probably it can't generate it at all. So yeah, the 3 is a good number of retries here. Okay, another problem here. I think on this slide, it's the best to start with an example. So we have a question from the user, who can swap shifts with me on Tuesday? And as a response, I just type the question marks, but probably the model will respond with something, yeah, with some query. But I'm 100% sure that that query would make no sense here, because it's really hard for the model to know what the swap shifts mean. Like, I don't know what the swap shifts mean. It's very specific for the given company, yeah. Because in the company where you ask this question, there may be multiple rules that need to happen to swap shifts with somebody. And so, of course, there are some obvious things, like probably you need to check the calendar of the person swapping shifts with me, but maybe these people need to have the same skill set, maybe they need to be from the same department, maybe they need to live in the same city, or maybe the person who covers my shift can't have more hours in the week than specified amount. So it's very, very domain and company specific knowledge. And the model doesn't know anything about it. So it may be required to add that extra knowledge, extra explanation into the model's context. So when the user asks the question about swapping shifts, you may provide the model with extra context, with extra instruction. What does it mean to swap shifts with somebody? What rules are needed to be confirmed here? And again, what you can use here is vector databases and embeddings. So you can dynamically select the context required for the model. And thanks that when the question is about swapping shifts and you have a lot of documents with rules, you can just grab the relevant parts and push it into the model's context. So that brings me to conclusion that maybe you don't want a large language model writing SQL at all. And it's pretty funny because my presentation is about large language models writing SQL, and right now I'm telling you that maybe you don't want to do this. But we had a different idea, and let's look into that. So often it happens that when you have a lot of users in your application and they are all asking questions from some categories of questions, because you have multiple use cases in your application and the user are asking the questions related to their work, probably, so what you can find in this question when you look into them, that a lot of times there are very similar questions asking about the same stuff. So for example, when we have, let's look at this group here on the bottom. Here we have question, who can cover my shift tomorrow? Who can swap shifts on Friday? Can't go to work today, anybody can cover. It's just different way of saying the same question. And what we can do is we can assign these similar user questions into groups. And for each group, we can create some sort of query template to respond to all the questions from that group with the same query template. So for all questions about shift swapping, we have one query template, maybe with some arguments, of course, but we have just one query template to answer all of that questions. And we can treat that query templates as tools available for the large language model. How it may work? We have another prompt for the model. So here in the system message, rather than saying that you have access to the database, we say that you have access to the following API. And after that, we specify all the query templates that we have in our system. You may think about them like about functions in Python. So they need to have a good name. They need to have a good names for the arguments, probably argument types, and sometimes you may add extra description saying what exactly this function does. And after listing all of our functions, all of our query templates, we instruct the model to suggest what functions should be called to answer the user question. So taking our example with covering shift, we have a question, who can cover my shift on Tuesday? And all the model did here, it's suggested to call the recommend shift swap function with a date for next Tuesday. And what we can do with this, we can grab that suggestion. So we know which query template to use because we have recommend shift swap. We have a query template for that, and we can just grab the arguments from the function call and put it into the query. Here on the right, I have maybe not very complex query, but still here you have some joins, you have inner query, but you can imagine in this example, I can have all these multiple conditions that user needs to comply with to cover my shift. So checking department, checking calendar, and checking all the hard stuff that would be really hard for the model to write an SQL query for. So what are the benefits of query templates? The first big benefit is that it's very easy to extract arguments for semantic search. So as I shown you in the second lesson with the semantic search, all that step with extracting the constant values from the query, you don't need that because here you have direct access for all the arguments. You have no SQL injection risk. Because you have full control of your queries. And next thing is really important. You know, output schema is well known for each query template. And why it is important? In the classical text to SQL result, you don't really know what the schema, what the results are. And if you want to somehow visualize it to the user, you probably need another call for the LLM. Hey, is that data makes sense to show that data, for example, on the graph or maybe in a table or something different? Here, when you have a set of query templates, for each query template, you can have custom logic of displaying it to the user. And still, of course, you won't be able to answer all the questions with the query templates. Because you can't predict all the possible questions from the user. But even if you can handle 80%, 60%, or even less with the query templates and the reminder with the text to SQL, you will still get a much better accuracy for your application as a whole. So it's even if it's some part of your questions, it's still better to handle this part of the questions by the query templates and the reminder with the classic text to SQL. Okay, but what if the question is more complex? Let's look at this question. Which clients in New York or Detroit are in the loyalty program? And let's break it down. So here we have three conditions, yeah, because we have condition for the city. It needs to be either New York or Detroit, and we have some condition for the loyalty program, whatever it means. And it would be really hard for you to create query templates to handle such question, because either you will need a lot of query templates or query templates with a lot of arguments. And it's not something that we want in our system. But we thought how to handle it a little differently. So what we did is we introduced a way of chaining the functions together. So here we have still functions. For each function is responsible for only one component of the question. So we have function like from city, and here we have New York. We have from city Detroit, and we have eligible for loyalty program. And these functions are joined together with the logical operators. So we have ors, we have ands, we may have nots here. And what you can do with something like this, what you can do is you can parse that. We parse it by to the abstract syntax tree format. And after parsing it, we got something like that. So it looks a little scary, but actually it is really cool. It's just a representation of this natural language, this intermediate query language in the Python code. And from that, we can transform that tree into the query. And how does it work? Each component, so each function, has its own little chunk of the query. It controls like this little chunk of the query. So here, the function from city with argument New York created that line, from city with argument Detroit created that line, and last function eligible for loyalty program created these two lines, because actually the loyalty program means that you need to have more than 3 orders and you need to join to our client database. At least you need to be a client for at least 1 year. And we have this these parts, these chunks, linked together by the ands and ors. So we called that thing that you generate from the question, we called that intermediate query language, and this is our approach to the text-to-SQL problem. And what are the benefits here? One of the benefits is it is faster and cheaper than generating the SQL queries. And it is because usually the intermediate query language is more concise than SQL. Just you generate less tokens. It is technology agnostic. From the same language, you can generate both SQL queries or maybe data warehouse extraction or even API calls. And the domain knowledge can be encapsulated. So here again, you had this eligible for loyalty program. It would be really hard for the model to generate these conditions because it doesn't know anything about our loyalty program in our company, but function code like that is really easy for understand to the model. And what I have been talking for the last few slides is our very own library, DBLI, which is now available on GitHub. It is open sourced, licensed under MIT license. So I really encourage you to scan this QR code. It will take you to our GitHub page. You can check it out. We have full documentation on our project, and maybe you will like it. So I think that's all. Thank you for listening, and thank you for your attention.